In this video, we're going to look at two examples of critical care situations. This first example states a 202-pound patient has a dopamine ordered at 6 micrograms per kilogram per minute. What's available to us is an IV bag containing 500 milligrams of dopamine, and it is contained in 300 milliliters. We need to determine, based on this order, what rate should we set the pump to. Now, dimensional analysis is going to be our main method for completing these problems because we are given an order in micrograms per kilogram per minute, and we need to figure out if the patient is ordered something, a certain number of micrograms for every kilogram that they weigh, for every minute. We need to determine, using our conversion factors, what should we set the pump to in milliliters per hour. So really there are a few things that need to be done here, and if we are just looking at the units of where we're starting and where we're going, the first thing that's pretty obvious is this per kilogram. And as we saw with dosage based on weight, we do need to eliminate this amount of kilograms. So we need to eliminate the per kilogram, and we used to refer to this, as we did earlier in the course, as customizing. We customize the order for this patient. So by multiplying by the patient's weight, we can eliminate kilograms and figure out the total number of micrograms per minute. So that's what we're going to do first. But then we're left with a few other things that need to be done still. We need to somehow get from micrograms to milliliters. And in previous problems, we were given an amount of mass to administer, so milligrams or micrograms or grams, and it needed to be administered via an IV. And we did this by looking at what was available to us. And if we look at the IV bag up above, we see we have milligrams to milliliters. So just looking at that, I'm thinking to myself, I'm going to need to convert micrograms to milligrams first, and then I'll be able to go into milliliters. And once we do that, so if we can get rid of the kilograms, get rid of the micrograms, the last thing to do will be to convert minutes into hours. So there's a lot going on in this problem, but if you are comfortable with dimensional analysis, it truly is no different than many of the problems we've already seen in this course. And I'm going to start by writing down what it is I want to convert, and that is the dose. So the dose that needs to be administered, what must happen is the patient needs to be given 6 micrograms per kilogram per minute. And the first thing I wrote up here was, if we need to, when we're done with our dimensional analysis, have milliliters per hour, we need to first get rid of this per kilogram, and I can do that by multiplying by the patient's weight in kilograms. So let's see, what is the patient's weight in kilograms? I am told up above that the patient weighs 202 pounds. So a very common first step in many of these problems is to, if the patient's weight is given in pounds, we'll need to convert that to kilograms. And we've been doing this throughout the entire course here. So if you are familiar and comfortable with just dividing by 2.2, please do that. If you're still a little uncertain about that, set up the dimensional analysis, set up a proportion, but just taking 202, dividing by 2.2, we're going to get our patient's weight in kilograms. We know that this is going to be rounded to the tenths place, so I'm going to write approximately 91.8 kilograms. That's the patient's weight, converting it to kilograms. So that's what I will multiply by. And when I do that, kilograms will cancel, and if I were to stop right now, I would know the total number of micrograms the patient needs to receive every minute. But that's not what we want, so I'm going to continue. I need to convert this micrograms into an equivalent number of milligrams, so I can use the availability in terms of the bag. I can use the milligrams to milliliters conversion factor. And I know 1 milligram is equivalent to 1,000 micrograms. If I were to stop right now, I would know the total number of milligrams per minute the patient would be receiving. Not what I want, so now I want to cancel out milligrams. Milligrams needs to be in the denominator to cancel it out. And I'm going from milligrams to milliliters. That is 500 milligrams. is contained in 300 milliliters. If I were to stop right now, what would I have? In the numerator, I would have milliliters, which is exactly what I want. So I'm going to circle that. I don't want to do anything else to that. I don't want to cancel out milliliters. That's what I want. Milliliters per minute, we're almost there. I don't want milliliters per minute. I want to cancel out minutes. And I want to go into hours. Because we know the pump is typically going to be a measure of milliliters per minute. Or excuse me, milliliters per hour. So that's what I'm looking for. So multiplying by 60 over 1 will give me milliliters per hour. Now we have in these problems typically, and as we'll see actually in this entire module, is there are dimensional analysis strings here where we have a lot of products. We're multiplying a lot of things. So this is where I like to just go and multiply all the numerators. So I'm going to multiply 6 times 91.8 times 300 times 60. I'm going to write that down. I think this is a good habit to get into, especially with the critical care and titration problems, is to go ahead and just multiply all of the numerators. And now I'm going to multiply all of the denominators. So 1 times 1,000 times 500 will be 500,000. That is something that I like to do, especially when we get to titration. This will make a little bit more sense of why we're doing that. And now if I put that ratio there into the calculator, we get exactly, so I'm going to write out exactly what I get. I get 19.8288. That's the exact answer in milliliters per hour. But we are setting an IV pump. So this is a good habit, once again, to get into. Write what you see on your calculator screen and then round. So we know with the IV pumps, we need to go to the tenths place. So this will be 19.8 milliliters per hour. So just reflecting back, very similar to many of the other dosage calculations that we've seen in this course. I'm given an order of something the patient must receive, and I need to convert it into something different than what it's in. So I need to convert micrograms per kilogram per minute into milliliters per hour, right? The IV rate is the milliliters per hour. So I made a plan of what I was going to do. I set up my dimensional analysis and found the milliliters per hour rounded to the tenths place. Let's look at one more example. This problem states we need to administer this medication, I'm not even going to try to pronounce that, nitromicide, 4 micrograms per kilogram per minute. This is through an IV. It's for a female patient weighing 138 pounds, and we know what's available to us. We have 100 milligrams of this medication and 250, that should say mLs. So there are 250 mLs of D10W. So what you need to determine is the pump rate. What do you need to go over and set the pump so that the patient is receiving the appropriate dosage of 4 micrograms per kilogram per minute? This is very similar to the last problem. So if you do want to pause the video and try this on your own, please do. But I'm going to jump right in. I need to get from micrograms per kilogram per minute into, when I'm done with my dimensional analysis, milliliters per hour, because we are working with an IV pump. So just as we saw in the last example, I need to multiply by the patient's weight, use what's available in my understanding of the metric conversions in order to get to milliliters per hour. So I'm going to start by writing the dose, 4 micrograms per kilogram per minute. And we know with all weight-based dosage, we need to multiply by the patient's weight in order to customize it for this particular patient. Up above, I'm told the patient weighs 138 pounds. I need to convert that to kilograms because the dose is in micrograms per kilogram. So I will divide by 2.2, and I'm going to round to the tenths place. So when I take 138, divide it by 2.2, I get approximately, if we round to the tenths place, 62.7 kilograms. So that's going to be what I multiply by. And if I multiply by 62.7, kilograms will cancel. And now we just want to continue with the dimensional analysis. The dosage is in micrograms but the availability of this medication is in milligrams, so I need to first convert micrograms into milligrams. We know there are 1,000 micrograms in 1 milligram, and now that I would, if I stopped there, have a unit of milligrams, we can go into milligrams into milliliters using what's available to us. We see there are 100 milligrams contained in the 250 mLs. So by multiplying by these conversion factors, I would have milliliters per minute. The last thing I need to do is to multiply by a conversion factor of minutes over hours. 60 minutes in 1 hour. We'll cancel minutes, go into hours. I am now ready to multiply all my numerators and all my denominators. So 4 times 62.7 times 250 times 60, we get a large number, 3,762,000. And in the denominator, all of them, we have 1 times 1,000 times 100 times 1 gives me 100,000. So when I find that quotient, we get exactly 37.62, and that's milliliters per hour. That's the exact quotient, right? That's when I take this 3 million number and divide it by 100,000, I get exactly this. But what should we set the pump to? This is not what we would set the pump to. We know when we were talking about IV pumps in Mat 150, we're going to round this to the tenths place. So what would I set the pump to? I would set the pump to 37.6 milliliters per hour.